Well, welcome to this short nudge video for MOP 7 in the Sound and Music unit. MOP number 7 is going to be kind of a carryover from MOP 6. MOP 6 was about recognizing the kinds of standing wave patterns that are associated with string instruments. And the main requirement there is that you have a node at each end where the string is fastened down. And then there's a number of harmonics that you can have from the most common, loudest, called the fundamental or first harmonic, and then all the higher harmonics after that. Now we're going to look at the math associated with this. So in this particular question, we see a standing wave pattern for a guitar string, and one important thing to remember is the name of these particular standing wave patterns. The one shown on the screen here has 3 of the loop shapes, and that's called the third harmonic for this particular string. The first question they're going to ask you is what the wavelength of this is. Now there's different ways to get the wavelength, but if you look at the information that's given here, we're given the speed of the waves on this string, 436 meters per second, and the frequency associated with this particular wave pattern is 812 hertz. So how do you get a wavelength from a speed and a frequency? Well, that of course is the equation we've been using since the last unit, which is what I call the wave equation, and that is speed is frequency times wavelength. So that will get you the wavelength here. Now something that catches people a lot on this is notice that this is going to give you the wavelength in meters because the speed is in meters per second and the frequency is in hertz. But they want the wavelength in centimeters. So keep in mind there's 100 centimeters for every 1 meter. So that's going to be a fairly high number. They give you this hint here that they want it in centimeters too. So once you have that wavelength, then it's time to figure out the length of this particular string. Well, here's the next important thing to remember. Every complete wave consists of a crest plus a trough. So on this particular pattern, I'm going to trace out crest and trough, and it's going to look like this. Up and down and back up again. So that is only 2/3 of the string. So the length of this string is actually longer than the wavelength. So there's a number of ways to do this, but my suggestion is you take that wavelength, divide it by 2/3, because this is 2/3 of a wave, and then you'll get how long the length of the string is. An alternative to that would be to multiply the length of this wave by 1.5, because you need 1.5 of those wavelengths to make the entire length shown here on this wave pattern. So either way you get that, you're going to find that the length is longer than the wavelength. Now in some of the other MOP questions, you're going to have patterns where the wavelength may actually be longer than the length of the string instead of shorter. So just always make sure before you click OK that you be sure that the one that's supposed to be longer is actually longer. So I think between those two relationships, between the diagram itself and the wave equation, you should be able to answer this kind of question and all the similar questions that you'll find in MOP 7. Good luck, and find me if you need any additional help.